Hello and welcome to our presentation. We are the control crew and our project is the rotary inverted pendulum. Our team members consist of David Batista, Dylan Carrillo, Erica Del Mundo, and Cesar Gomez. Here is a brief overview of what we will be discussing about our project today. Our project's motivation was to deepen our understanding of control systems by working with a dynamic and real-world problem. The rotary inverted pendulum is a perfect technology to use as an educational platform. Some key aspects of the rotary inverted pendulum are feedback control, system dynamics, and real-time microcontroller implementation. Our project is compatible with MATLAB and Simulink, making it easy to access for students.
Our system is built using 4 core hardware components that work together to control and measure the rotary inverted pendulum. First, we use the STM32 Nucleo microcontroller. This board serves as the main brain of our system, running our dual PID controllers, reading encoder signals, and sending motor control commands in real time. Next, our motor driver is driven using the DFR0601 5-amp motor driver. This driver provides the necessary current and voltage to power our high-torque DC motor while maintaining stable and precise control. For accutation, we selected the Polulu 47-1 high-power gear motor. This motor includes a built-in 48 counts per revolution quadrature encoder, giving us accurate shaft position feedback for the swing up and balancing controllers. Finally, we use an external 2400 CPR incremental rotary encoder mounted directly on the pendulum arm. This encoder gives us a high-resolution measurement of the pendulum angle, which is essential for stable inverted position control. Together, these components provide the sensing, computation, and power delivery required for real-time feedback control of our rotary inverted pendulum.
The microcontroller continuously measures 2 key signals, the pendulum angle and the motor voltage. These signals are streamed live into MATLAB Simulink, where we can observe the system response in real time and adjust our controller gains during testing. For the control design, we apply standard feedback control practices used throughout industry and in our coursework. This includes root locus analysis to understand the closed-loop pole locations, calculating proportional, integral, and derivative gains based on specifications like settling time and damping ratio, and linearization, the pendulum's dynamics around the upright equilibrium to design stabilizing controller. By combining 2 dual PID controllers with real-time Simulink visualization and classical control system tools, we create a complete and reliable framework to swing the pendulum up and maintain it inverted.
This is the 3D model of our rotary inverted pendulum system, designed in SolidWorks. The structure consists of a vertical base frame that supports the main mechanical assembly. At the center, you can see the Pololu 12-volt DC motor mounted on a custom bracket. This provides the rotational motion for the pendulum arm. Attached to the motor shaft is a flexible coupling that connects to the rotary arm, allowing smooth torque transfer while minimizing vibration or misalignment. At the far end of the rotary arm is our TICE incremental encoder, which is mounted to precisely measure angular displacement. This encoder provides real-time feedback to the control system for balance stabilization. The pendulum rod is connected at the tip of the rotary arm, representing the unstable element that the controller will balance at its upright position.
This is an image of our STM32-767ZI microcontroller pin activation diagram. This image was set on the STM32 Cube IDE system software. We began by activating 2 GPIO pins PG3, PG2, used for motor directional control through our motor driver. 4 timer pins, timer 1, timer 2, and timer 8, timer 13. Timer 1 and timer 2 were used as encoder inputs, while timer 8 was a pulse width modulation for our motor, and timer 13 was used for periodic interrupts to send encoder data. USART was used for asynchronous data transmission through our USB. Here's an image of our microcontroller code used for taking inputs from the MATLAB and sending out counts of both encoders every millisecond. Here's some of the data outputs we got by moving both the encoder attached to the motor and the encoder by itself, along with the Simulink used to control the motor manually and receive those encoder counts per revolution.